This is the Math 2 lesson summary video for the lesson entitled Similar Triangles. In Lesson 3 of Unit 7, Similar Triangles, the purpose of this lesson is to solidify the concepts of similarity for polygons and prove triangles similar by angle-angle similarity, side-angle-side similarity, and side-side-side similarity theorems. The vocabulary included in this lesson includes the angle-angle similarity theorem, which means we need two corresponding angles in two different triangles to be congruent in order to conclude the triangles are similar. Another way that we can prove that they are similar is if we use side-angle-side similarity theorem. We have two sides in two different triangles that have the same ratio, and the angle in between the sides is congruent. And the last one is what we call side-side-side similarity theorem. If all three sides in two different triangles have the same ratio. To review from the previous lesson, we will also be using our properties of similar figures in this lesson. The first property is that corresponding angles in similar triangles are always congruent, and corresponding side lengths in similar triangles will always have the same ratio. In Lesson 3 of Unit 7, we are solidifying our knowledge of similar triangles and will discover in this lesson 3 ways to prove that triangles are similar. We are going to start with problem 2 of this lesson. While for polygons in general, we need to know all corresponding sides are congruent and all corresponding pairs of sides are proportional before we can say they are similar, it actually turns out we can tell triangles are similar with a lot less information. In the first part of this lesson, we are given the definition again of similarity. Two figures are similar if the second can be obtained from the first by a sequence of rotations, reflections, translations, and dilations. We will be using this definition throughout this investigation to prove our shortcuts to prove triangles are similar. We're going to skip to part 2, but in part 2 we're going to use conjecture 1, which states that all equilateral triangles are similar. In part 2, Mia is explaining to Mason why she thinks conjecture 1 is always true. Remember, conjecture 1 states that all equilateral triangles are similar. Analyzing Mia's thinking, we can see that she knows that in an equilateral triangle, all the angles are 60 degrees. Therefore, in my diagram, each of these angles would be 60 degrees. That is by definition of an equilateral triangle. If all the sides are congruent, all the angles must be 60 degrees. By our definition of similarity from previous lessons, we know that two figures are similar if the second can be attained from the first by a sequence of rotations, reflections, translations, and dilations. So what we're going to try and do is get this triangle on the left to coincide or overlap somehow by one of our transformations to the triangle on the right. Mia's explanation that the triangles are similar includes first translating and rotating triangle ABC until this vertex A coincides or lies on top of vertex Q. That would be the first transformation that she's discussing in her explanation. Then she says, since A and Q are both 60 degrees, which we can see they are, so they are equal in measure, side AB will lie on top of side QR. So what I'm going to do is I have this initial triangle over here, and so A, if I coincide A with Q and show you what that might look like, it will look something like this. So A is lying on top of Q, and then we do notice that point B from our original triangle, which is here, will end up on side Q, and it's hard to tell there. Is that an R? Yeah, and our initial value of QR. So side AB will lie on top of QR. Side AC, notice, lies right on top of side QS. If we dilate the initial triangle from the left that I've just overlapped on the right, if we dilate that smaller triangle ABC with point A at that center of dilation, which is here, until B and C coincide with points R and S. So what that would mean is this B would move, dilate so it overlaps with that R, and this C would move so it overlaps with this S. So we would dilate, we would want to multiply by a scale factor that's greater than 1. So we've just explained how then we know that these two triangles will be similar. In 3, we are asked if Mia's explanation convinces us for sure that triangle ABC is similar to triangle QRS based on our definition of similarity from the previous page, which I did highlight, which was, or I didn't highlight, but which was here, okay, that we've used in previous lessons. If we can translate that point A so that it lies on top of point Q, and we can dilate side AB so that B lies on top of point R, then the two triangles will be similar because we can show that they are congruent based on a set of transformations. So in this case, yeah. So yes, we can show that the two triangles are similar because we can show they are congruent based on a set of transformations. So if we are able to show that they are congruent based on a set of transformations, then the triangles have to be similar. So reflecting upon what information we were given in number 2, we were given only that 3 corresponding angles were congruent, and we were able to determine that the triangles were similar. So now let's look at a formal proof on the next page, scrolling down to number 7, conjecture 3, that any two triangles are similar if their corresponding angles are congruent. So what we are given, the first thing we need to do is mark the given. We are given that angle A is congruent to angle D. We are given that angle C is congruent to angle F. We are given that angle B is congruent to angle E. So notice we're given the same information from the previous example. We are given that all 3 corresponding angles in a triangle are congruent. And we're asked to determine if the two triangles are similar. Notice that little symbol means similar, and explain your reasoning. So if we think about our transformations from the previous one, we can translate point A so that it coincides with point D. Then what will happen is side length AC, which is here, will lie on top of side length DF, and point C will be somewhere on line segment DF. Likewise, segment, I'll use a different color, AB will lie on top of segment DE, where point B will lie somewhere on line segment DE. Using our same information, if we then perform a dilation to get point C to coincide with point F and point B to coincide with point E, then the triangles are congruent. And if the triangles are congruent, we then can say that they're similar based on the information we discussed in the last example. So let's now talk about what information we actually knew. We were given 3 angles, but what if we are only given 2 angles? Do we know that the third angle will be congruent? And the answer to that is yes, because if this angle is 30 degrees and angle B and E, let's just say is 60 degrees, we know then the remaining angles for both of these triangles must be 90. So the minimum amount of information needed to prove that these triangles are congruent are actually only 2 corresponding angles. And in math, we call this the angle-angle similarity theorem. So if we know 2 corresponding angles in 2 different triangles are congruent, we can conclude then the triangles are similar. So we're now saying we don't need to know all the angles and all the sides in 2 triangles to determine they're similar. If we only know 2 angles that are corresponding are congruent, we can conclude the triangles are similar. So let's move to conjecture 4. We are told in conjecture 4, we are asked if any 2 triangles are similar, if only 2 pairs of sides are proportional. So what that means is, I'm going to make this come to life, but AP, they're saying, is equal to DP times the scale factor. So I'm just going to make a length for DP. Let's just say the length of DP is 3, and the length of CP is 4. Okay, now looking at this diagram, we do know that these 2 angles will be congruent because they're vertical angles, and they're saying that the length of AP, which is here, will be the length of DP times a scale factor K. So let's just choose a K. Let's just say the scale factor is 2, which means we're performing a dilation. So let's multiply 2 times 3 and say that this side is 6. And then they're saying that CP times that same scale factor would give us the length of BP. So 4 times 2 is 8. And then we're asked, can we determine based on this information that these 2 triangles are congruent? Well, we can discuss our information with our transformations and the same way we did in the previous 2 examples, and we will be able to prove that they are congruent that way. We are going to flip to just our theorem, which tells us that if we have a side, an angle, and a side, and the angle is congruent in between the 2 sides, if the 2 triangles are similar, they have 2 pairs of corresponding sides that are proportional, and the included angles are congruent. So what this means is, there's my congruent angle in red, and if we take our side lengths, we were comparing 3 to 6, and 4 to 8. If we get the same scale factor, then we know that these 2 triangles are similar. So 3 to 6 can be simplified to 1/2. 4 to 8 can be simplified to 1/2. So because we get the same ratio, that means that these triangles are similar. So the second method that we use to prove triangles similar is what we call side-angle side similarity theorem. We will need to show that one angle is congruent to each other, and the other 2 sides around the angle have the same ratio. We have one more way to prove that triangles are similar, and the last method is when any 2 triangles have all 3 sides that are proportional. We call this the side-side-side similarity theorem. So 2 triangles are similar if all 3 pairs of corresponding sides are proportional. So what that means is that if we take a side length, and we know all the side lengths on all 3 sides, let me switch that around. and no, I'm making these up. Okay. So now let's take a look. Corresponding sides, SQ over XZ. So let's write out our ratios based on these at the top. So SQ is 8, XC is 4. That needs to equal QR 7 over ZY 14. I'm sorry, I need to flip these two. That's what happens when you make them up on the spot. So I'm just gonna say that side's 14 to 7, and QR over, I'm sorry, that should be SR over XY. We're missing SR over XY because we have to find the ratios of all three sides. So SR over XY. So let's simplify those. We get 2, 2, and 2. If we get the same ratio or scale factor among two triangles, if we only know the sides, then we can conclude the triangles are similar. So we've just discussed 3 ways in which we can prove triangles are similar. The first way is angle-angle similarity theorem. The second way is side-angle-side similarity theorem. And the third way is side-side-side similarity theorem. We do not need to know that all the corresponding angles and all of the corresponding sides are congruent or have the same ratio. This is enough information to prove that triangles are similar. If you need more help on the Ready, Set, Go homework for this task, please check the Canvas Student Support site.